Welcome! In this video, we'll be tackling LeetCode problem number 1710, titled Maximum Units on a Truck. This problem challenges us to maximize the number of units we can load onto a truck, given a set of constraints. It's a great exercise for honing your problem-solving skills and understanding optimization techniques. Let's dive in. In this problem, we are tasked with loading a truck with as many units as possible. The truck has a specific maximum capacity, measured in the number of boxes it can carry. You are provided with a list of box types, where each type tells you two things: the number of boxes available of that type and how many units each box contains. Your goal is to maximize the total number of units loaded onto the truck without exceeding its capacity. The input for this problem consists of a 2D array called box types, where each subarray provides the number of boxes and the units per box for a specific type. Additionally, you are given an integer truck size, which represents the maximum number of boxes the truck can carry. The output will be a single integer, representing the maximum total units that can fit onto the truck. Let's explore a few examples to better understand how this works in practice. In the first example, we have three box types, one with one box containing 3 units per box, another with 2 boxes containing 2 units per box, and a third type with 3 boxes containing 1 unit per box. The truck has a capacity of 4 boxes. To maximize the number of units loaded, we start by selecting the box type with the highest units per box. First, we take one box of the type that has 3 units per box, which adds 3 units to our total, leaving space for 3 more boxes. Next, we take 2 boxes of the type that has 2 units per box, adding 4 more units to our total, with room for 1 more box. Finally, we take one box of the type that has 1 unit per box, adding 1 more unit to our total. This gives us a maximum of 8 units loaded onto the truck. Now let's look at a second example to further solidify our understanding. In the second example, we have 4 different box types with various units per box, and the truck can hold up to 10 boxes. We start by selecting the box type with the highest units per box, which is 9. We take 3 boxes of this type, adding 27 units to our total, leaving space for 7 more boxes. Next, we take 4 boxes of the type with 7 units per box, adding 28 more units, with room for 3 more boxes. After that, we take 2 boxes of the type with 5 units per box, adding 10 units, leaving space for just 1 more box. Finally, we take 1 box of the type with 10 units per box, adding 10 more units to the total. This brings the maximum number of units loaded onto the truck to 91. This example illustrates the importance of prioritizing box types with the highest units per box. Let's now discuss some constraints and edge cases to consider. When solving this problem, there are several constraints and edge cases to keep in mind. First, if the truck's capacity is larger than the total number of boxes available, you can simply load all the boxes. Second, if all box types have the same number of units per box, the solution is simply determined by how many boxes can fit within the truck's capacity. If the truck can only hold 1 box, you should select the box type with the highest units per box. If no boxes are provided, the result is 0. Lastly, if the boxes perfectly fit the truck's capacity, you can directly sum the units from all the boxes. To solve this problem efficiently, the recommended approach is to first sort the box types in descending order based on the number of units per box. Then, you can use a greedy strategy to pick boxes from the highest unit per box type, adding them to the truck until it is full or there are no more boxes left to load. This method ensures that you achieve the maximum total units possible. To solve this problem, one possible method is the brute force approach. In this strategy, we would attempt to evaluate all possible combinations of boxes to determine the maximum number of units that could fit in the truck. The idea is to exhaustively explore every possible arrangement of boxes, either through recursion or iteration, to find the optimal solution. However, this approach is highly inefficient. The time complexity grows exponentially, specifically 2 to the power of n, where n is the number of box types, as we need to evaluate all possible subsets. Additionally, the space complexity is n, accounting for the recursion stack in the worst case. While this method guarantees the correct result, it becomes computationally impractical for larger inputs. Given the constraints of this problem, such as the potential for n to be large, this approach is not feasible and is therefore rejected in favor of more efficient solutions. A much more efficient alternative is the greedy approach, which is optimized and practical for this problem. The idea here is to prioritize loading the most valuable boxes first by sorting the box types based on their units per box in descending order. Once sorted, we iterate through the list and add as many boxes as possible of each type, stopping as soon as the truck's capacity is reached. This ensures an efficient and direct solution. The steps include sorting the box types, initializing a counter to track the total units, and iterating through the sorted boxes to add them while deducting from the truck's remaining capacity. The greedy approach works because it aligns with the goal of maximizing units. By always choosing the highest value boxes first, we avoid unnecessary computations. With a time complexity of O(n log n) due to sorting in O(n) for iteration, this method is significantly more efficient than brute force. Additionally, the space complexity is O(1), as the sorting can be done in place. For this problem, the greedy approach stands out as the most logical and efficient choice. The greedy approach is ultimately the chosen strategy because it strikes a balance between efficiency and simplicity. By sorting the box types by their units per box, we can directly prioritize the most valuable boxes, ensuring we maximize the number of units loaded onto the truck without unnecessary overhead. The iterative process further ensures that the solution is both systematic and efficient, stopping as soon as the truck's capacity is filled. This significantly reduces computational effort compared to the brute force approach. A key observation here is that the problem essentially reduces to sorting and selection, which the greedy strategy handles naturally. While this method works perfectly under the given problem constraints, it is worth noting that additional constraints, such as weight limits, might require modifications to the approach. Overall, the greedy strategy guarantees the optimal solution for this problem while remaining computationally practical and intuitive to implement. This problem is about maximizing the number of units we can load onto a truck, given its limited capacity. Each box type specifies two things: the number of boxes of that type and the number of units each box contains. The objective is to determine how we can load the maximum possible units without exceeding the truck's capacity. To achieve this, we can break the algorithm into a few clear steps. First, we parse the input, which consists of a list of box types and the truck's capacity. Then, we pre-process the box types by sorting them in descending order based on the number of units per box. This sorting step is crucial because it ensures that we prioritize the most valuable boxes first when loading the truck. Sorting the list takes O(n log n) time, where n is the number of box types, and this optimization forms the foundation for the rest of the solution. Now that the box types are sorted, the next step is to iteratively load the boxes onto the truck. We start by initializing two variables, total_units, which tracks the total units loaded so far, and remaining_capacity, which keeps track of how much space is left in the truck. Both are set to 0 and the truck's capacity, respectively. Then, for each box type, we determine how many boxes to load. This is done by taking the minimum of the available boxes of that type and the truck's remaining capacity. Once we know how many boxes to load, we update total_units by adding the units contributed by these boxes, and we reduce the remaining_capacity accordingly. If the truck becomes full, meaning the remaining capacity reaches 0, we stop processing further box types early to save unnecessary computations. Finally, when all applicable boxes are loaded or the truck is full, we return the value of total_units, which represents the maximum units that can fit on the truck. The key to solving this problem lies in making a greedy choice at every step, which ensures that we maximize the units loaded. By sorting the box types in descending order of units_per_box, we guarantee that the most valuable boxes are loaded first. This approach works perfectly for this problem because our goal is to maximize the sum of units, and higher value boxes contribute more to that objective. Additionally, the early termination condition allows us to stop as soon as the truck's capacity is exhausted, saving time and unnecessary calculations. There are also several edge cases to consider. For instance, if the truck's capacity is 0, no units can be loaded, so the result is 0. Similarly, if all box types have 0 units per box, the result will also be 0 regardless of the capacity. Lastly, if the truck's capacity exceeds the total number of boxes available, we simply load all the boxes, and the result will be the sum of units from all box types. To implement this algorithm, we use straightforward data structures. The input list stores box types as pairs of number_boxes, units_per_box, and we use two variables, total_units to keep track of the total units loaded and remaining _capacity to monitor how much space is left in the truck. The algorithm's efficiency is also worth noting. The sorting step has a time complexity of O, n log n, and iterating through the box types takes O, n, so the overall time complexity is O, n log n. In terms of space complexity, the sorting is done in place, meaning we only require O(1) additional space. This makes the solution highly efficient both in terms of time and memory usage. Let's walk through an example to see the algorithm in action. Suppose the input consists of box types 1, 3, 2, 2, 3, 1, and the truck's capacity is 4. First, we sort the box types by units_per_box in descending order. In this case, the list is already sorted, so no changes are needed. Next, we start loading the boxes. From the first box type, 1, 3, we load one box, adding 1*3 equals 3 units to the truck. The remaining capacity is now 4, 1 equals 3. From the second box type, 2, 2, we load two boxes, adding 2*2 equals 4 units. The remaining capacity becomes 3, 2 equals 1. Finally, from the third box type, 3, 1, we load one box, adding 1*1 equals 1 unit. The truck's capacity is now full, with no space left. The total units loaded onto the truck is 3 plus 4 plus 1 equals 8, and this is the result of the algorithm. In conclusion, this algorithm effectively maximizes the units loaded onto the truck by leveraging a greedy approach. By sorting the box types based on units_per_box and prioritizing the most valuable boxes, we ensure an optimal solution. Additionally, the early termination condition allows us to save computation time by stopping as soon as the truck is full. With a time complexity of O, n log n, and minimal space usage, this solution is both efficient and practical for real-world scenarios. The step-by-step execution and edge case handling further demonstrate the robustness of this approach. This Python implementation solves the LeetCode problem number 1710, maximum units on a truck, efficiently using a greedy algorithm. The goal is to maximize the number of units loaded onto a truck, given the constraints of limited capacity. First, the maximum units function accepts two inputs, box types, a list of pairs where each pair represents the number of boxes in units per box, and truck size, the maximum capacity of the truck in terms of boxes. The algorithm starts by sorting the box types list. The sorting is performed in descending order based on units per box using a lambda function, key equals lambda xx, 1, reverse equals true. This ensures that the most valuable boxes, in terms of units, are considered first. Next, we initialize total_units to 0. This variable will track the cumulative number of units loaded onto the truck. The code then iterates through each box type in the sorted list. For each box type, it checks if the truck still has capacity. If the truck is already full, truck size equals 0, the loop breaks early to optimize performance. Inside the loop, the algorithm decides how many boxes to take from the current box type. It uses the min function to ensure that it doesn't exceed either the available boxes of that type, box_count, or the remaining capacity of the truck size. The number of units contributed by the selected boxes is calculated by multiplying boxes_to_take with units_per_box, and this value is added to total_units. The truck's remaining capacity is then reduced by boxes_to_take. Finally, after processing all box types, or filling the truck, the function returns total_units as the result, representing the maximum number of units that can be loaded onto the truck. This solution is efficient, with a time complexity of O, n log n, due to the sorting step, where n is the number of box types. The subsequent iteration through the list has a linear complexity of O, n, making the overall approach optimal for this problem. Here, we begin by importing the necessary libraries and defining our solution class. The main method, maximum units, takes two parameters, a 2D array box types and an integer truck size. The goal is to maximize the total number of units that can be loaded onto the truck, given its size limit. First, we sort the box types array in descending order based on the number of units per box. This ensures that we prioritize boxes with the highest units. Next, we initialize a variable total units to keep track of the cumulative units on the truck. The for loop iterates through each type of box in the box types array. For each box type, we extract the number of boxes available and the units per box. If the truck is already full, we exit the loop early. Otherwise, we calculate how many boxes of the current type we can take, which is the smaller value between the available boxes and the remaining truck capacity. Finally, we add the units contributed by these boxes to total units and reduce the truck's remaining capacity accordingly. After the loop, we return the value of total units, which represents the maximum number of units that can be loaded onto the truck. This approach efficiently prioritizes boxes with the highest units per box while respecting the truck's capacity. By sorting the input and iterating through it just once, the solution achieves optimal performance, making it suitable even for larger inputs. In this problem, the goal is to maximize the number of units that can be loaded onto a truck. We're given a list of box types, where each type specifies the number of boxes available and the number of units contained in each box. Additionally, we have a truck with a limited capacity, defined by the number of boxes it can hold. To achieve the maximum units, we prioritize loading boxes that have the highest units per box first. For example, consider the input where we have box types as 1, 3, 2, 2, 3, 1, and a truck size of 4. The first step is to sort the box types based on units per box in descending order. Here, the sorted order remains the same: 1, 3, 2, 2, 3, 1. Next, we initialize our variables, total_units to 0 and the available truck size to 4. With this setup, we can begin processing the box types one by one to load as many units as possible onto the truck. Starting with the first box type, which has 1 box and 3 units per box, we calculate the number of boxes we can take. Since the truck's capacity is 4, we can take all 1 box. This adds 1 multiplied by 3, or 3, units to our total. We then decrease the truck's capacity by 1, leaving us with a truck size of 3. Next, we process the second box type, which has 2 boxes and 2 units per box. Here, we can take all 2 boxes, as the truck still has enough capacity. This adds 2 multiplied by 2, or 4, units to our total, bringing it to 7. The truck's capacity is now reduced by 2, leaving space for just 1 more box. Finally, we move to the third box type, which has 3 boxes and 1 unit per box. Since the truck can only hold 1 more box, we take just 1 box, adding 1 unit to our total. This brings the total number of units to 8, and the truck is now full with a capacity of 0. The final output for this example is 8 total units. Now, let's examine another scenario where the truck has a more limited capacity. For this input, we have box types as 5, 10, 2, 5, 4, 7, and a truck size of 5. As always, the first step is to sort the box types based on units per box in descending order. After sorting, we get 5, 10, 4, 7, 2, 5. With the box types sorted, we initialize total_units to 0 and the truck size to 5. Starting with the first box type, which has 5 boxes and 10 units per box, we determine how many boxes we can take. Since the truck can hold up to 5 boxes, we take all 5. This adds 5 multiplied by 10, or 50, units to our total. The truck is now full, with a capacity of 0, so we don't process any more box types. The final output for this example is 50 total units. In this next example, the truck has excess capacity compared to the total number of boxes available. Here, the input specifies box types as 5, 2, 3, 3, 1, 4, and a truck size of 10. Once again, we start by sorting the box types by units per box in descending order, resulting in 1, 4, 3, 3, 5, 2. With everything sorted, we initialize total_units to 0 and the truck size to 10. The first box type has 1 box with 4 units per box. Since the truck can hold up to 10 boxes, we take all 1 box, adding 1 multiplied by 4, or 4, units to our total. This leaves the truck with a capacity of 9 boxes. Next, we process the second box type, which has 3 boxes and 3 units per box. With the truck's remaining capacity of 9, we can take all 3 boxes. This adds 3 multiplied by 3, or 9, units to our total, bringing it to 13. The truck now has space for 6 more boxes. Finally, we move to the third box type, which has 5 boxes and 2 units per box. Since the truck has enough capacity, we take all 5 boxes, adding 5 multiplied by 2, or 10, units to our total. This brings the final total to 23 units, and the truck has 1 box of unused capacity. The final output for this example is 23 total units. To understand the time complexity of this solution, we start by analyzing the sorting step. Sorting the box types array, which contains n box types, is performed using Python's timsort algorithm. This is a comparison-based sorting method with a time complexity of O(n*log n). Once the array is sorted, we proceed to iterate over the box types. During this iteration, for each box type, we perform a constant time operation to calculate the minimum of 2 values, followed by basic arithmetic operations like multiplication and addition, which are also O(1). Since we process all n box types in the worst case, this iteration step has a linear time complexity of O(n). Combining these 2 steps, the overall time complexity of the solution is determined by the sorting step, resulting in O(n*log n). Now, let's analyze the space complexity of the solution. First, the input array, box types, contains n elements, each represented by 2 integers. This means the input inherently requires O(n) space. Next, the sorting step uses Python's timsort, which has an auxiliary space complexity of O(n). Beyond this, the solution uses a small number of additional variables like total_units and truck size, which require constant space, or O(1). When we combine these factors, the overall space complexity of the solution is O(n), primarily driven by the input storage and the sorting overhead. Let's examine the best, average, and worst case scenarios. The sorting step, which takes O(n*log n), is consistent regardless of the input order, so its complexity remains the same across all cases. In the iteration step, the best case scenario happens when the truck is filled before processing all box types. However, this doesn't affect the asymptotic complexity, as the sorting step still dominates the overall time. Similarly, in the worst case, the truck has enough capacity to process all box types, but the complexity remains O(n*log n). Even in the average case, the overall complexity doesn't change. To put this into perspective, a brute force approach that considers all possible combinations of box selections would have an exponential complexity of O(2 to the power of n). In contrast, the greedy algorithm optimally solves the problem by focusing on sorting and iterating, reducing the complexity to O(n*log n). This makes the greedy approach far more efficient and suitable for real-world scenarios. Finally, let's mathematically justify the big O complexity of the solution. The sorting step is O(n*log n), which is the standard complexity for comparison-based sorting algorithms. The iteration step, where each box type is processed exactly once, is O(n). When we combine these 2 steps, we add their complexities, O(n*log n plus O(n). Since O(n*log n grows faster than O(n), it dominates the combined expression, and the overall time complexity simplifies to O(n*log n). For space complexity, the input array and the sorting overhead dominate, resulting in O(n) space usage. This analysis confirms that the solution is both time and space efficient for this problem. When tackling this problem, it's important to be aware of some common mistakes that can lead to incorrect results or inefficient solutions. First, not handling edge cases properly, such as when the input list is empty or the truck's capacity is 0, can cause runtime errors or unexpected outputs. To address this, always validate your inputs and account for these scenarios before diving into the main logic. Next, inefficient sorting or redundant computations can unnecessarily inflate your time complexity. For instance, repeatedly sorting the input array or recalculating values like total units per box inside a loop can be avoided by pre-computing these values and using efficient sorting strategies. Lastly, misunderstanding the greedy approach can lead to suboptimal solutions. Instead of trying to distribute boxes evenly, Focus on maximizing the number of units by prioritizing the most unit-dense boxes. This ensures that you're always making the best local decision to achieve the optimal global result. Another common pitfall is failing to consider scenarios where the truck's remaining capacity is insufficient to fit an entire box. In such cases, skipping the box altogether results in wasted capacity. Instead, you should account for partial boxes by loading only as much as the remaining capacity allows. Additionally, using the wrong data structures can introduce inefficiencies. For example, relying on a simple list instead of a heap or priority queue can make accessing the most unit-dense boxes slower, especially in larger input sizes. To optimize your solution, choose data structures that align with the problem's constraints, such as using a max heap to easily retrieve the most profitable boxes. In interviews, it's crucial to articulate the reasoning behind your chosen approach. For this problem, using a greedy strategy is often the best option because the goal is to optimize for a single metric, maximizing the number of units. Be prepared to explain why dynamic programming, which is more suited for problems with overlapping subproblems, is unnecessary here. Another point to highlight is the trade-off involved in sorting the input. While sorting the boxes by units per box has a time complexity of n log n, this is typically acceptable. However, for larger datasets, a heap-based approach could be more efficient, as it allows you to manage the top k elements dynamically. Relating your solution to real-world scenarios, such as cargo loading or resource allocation, can also demonstrate a practical understanding of the problem, which is something interviewers often appreciate. To deepen your understanding of this problem, it's helpful to explore related problems that utilize similar techniques. For example, LeetCode 1710, the maximum units on a truck problem, is the direct problem we're discussing here. LeetCode 455, assign cookies, also involves a greedy algorithm where you aim to maximize satisfaction by efficiently distributing resources, in this case, cookies to children. Another related problem is LeetCode 406, queue reconstruction by height, where you use sorting and greedy reconstruction to solve a prioritization challenge. Finally, LeetCode 1029, two-city scheduling, is another greedy optimization problem that focuses on minimizing cost by optimally distributing resources between two groups. Practicing these problems helps solidify your understanding of greedy algorithms and their applications in different contexts. There are several approaches you can take to solve this problem, each with its own trade-offs. A brute force approach, where you try all possible combinations of boxes to find the maximum units that can fit in the truck, is conceptually simple but highly inefficient, with an exponential time complexity of 2 to the power of n. This method is only practical for very small input sizes or as a baseline for comparison. On the other hand, the greedy approach is much more efficient. By sorting the boxes in descending order of units per box and iteratively loading them, you achieve a time complexity of n log n, though additional logic is needed to handle partial boxes. For even greater efficiency in certain scenarios, a heap-based optimization can be used. With a max heap, you can dynamically manage the boxes with the highest units per box, which is especially useful when the input is unsorted or changes dynamically. While slightly more complex to implement, this approach offers a good balance between performance and flexibility. Great work! In summary, we used a sorting and greedy approach to solve the maximum units on a truck problem efficiently. Remember, mastering optimization techniques like these can give you an edge in interviews and real-world scenarios. Thanks for watching, and don't forget to subscribe for more problem walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!